Well, after that sarcastic comment, we'll start the video. Okay, so chemical thermodynamics. We've already kind of talked about this. This is some of the like delta H and all of that stuff that we've talked about, how heat affects a reaction. We're getting back into energy a little bit, but we're going to add some stuff to it now. You will recall from Chapter 5 that energy cannot be created or destroyed. That's the first law of thermodynamics. I don't know if we really talked about that in Chapter 5. I think we did briefly, but I'm going to kind of do here what I did in the first couple of sections of Chapter 5 as well. We're not going to spend a lot of time on it. There is some good foundational stuff there, but it gets a little bit more into the realm of physics, and they don't ask a lot of questions about it on the AP exam, so we'll go through this first part fairly quickly, okay? But if energy can't be created or destroyed, the total energy of the universe is a constant. That's a lie, but we're going to go with it, okay? In nuclear reactions, a little bit of matter is changed into energy, and so there is energy being created. You could really say a really correct statement would be the sum of the mass and the energy in the universe is constant, right? But in normal chemical processes, that is a correct statement, okay? Total energy is constant. It can also be converted from one form to another, one form of energy to another. So now we're not talking about nuclear reactions, but just normal chemical processes. Or it can be transferred to a system from surroundings or from surroundings to system, or, you know, I think I said the same thing twice there, but you know what I mean. So you guys remember all of that stuff, right? The heat transfer and all of that, and the transformations that can occur with energy. So now we need to talk a little bit about spontaneous processes, because a big part of this particular chapter in the book is looking at a reaction and deciding, is this going to happen on its own without outside intervention? Okay, and that's called the spontaneous process. So there are lots of processes in nature that are spontaneous, right? Things that will happen without outside intervention. Can you think of an example of a spontaneous process? And maybe a chemical reaction that happens without any outside intervention on our parts. You just kind of let it sit and it reacts. I don't know about, what do you mean by soda? Well, that's more of a, okay, I guess you could count that as a spontaneous process, because even a physical process can be a spontaneous too. I was thinking more in terms of chemical reactions, but this is an example of a physical process right here, so that works. So you open the soda bottle, right? At normal pressure, CO2 spontaneously comes out of the, I guess you could count that. What about you take a bite out of an apple and then just let it sit on your counter for a day or two? And that's a spontaneous chemical reaction, right? It's going to oxidize. It's going to turn brown. You know, cars after a certain amount of time. Now, spontaneity doesn't mean it happens immediately, right? It just happens without outside intervention. So over time, iron rusts. You know, that's an example of a spontaneous reaction. So it doesn't have to be fast. It just has to happen naturally without any outside intervention, okay? So an example of that, if you have a, you know, like this situation that happens all the time in your life, where you've got a complete vacuum on one side of a you know, these two bulbs here, they're connected with a stopcock, and then you turn the stopcock, and then, you know, fills both sides. That's a spontaneous process, okay? A gas will expand to fill a vacuum. That happens spontaneously, right? So if a gas is exposed to a vacuum, it will fill that area. Now, it is not spontaneous for a gas to create its own vacuum, right? So to go back in this direction, not spontaneous, because then all the gas would somehow on its own have to go back to side B, and then side A is a complete vacuum again. Obviously, that's not going to happen without outside intervention. Now, can we make it happen? Yes, but it takes energy to make it happen, okay? This just happens naturally on its own. And I should be careful with that, because, you know, even spontaneous processes require some energy to start because of our activation energy, right? But it doesn't need outside intervention for it to start. Okay, so the gas in vessel B obviously will spontaneously effuse into vessel A, but then it's not going to go back spontaneously. Okay, so another example, well, I mean, this is one of the examples I used, right? Spontaneous reaction is an iron nail rusting. If they're spontaneous in one direction, they are not going to be spontaneous in the other direction, okay? In other words, they are not reversible. Now, does that mean that it can never go back? Again, not necessarily, but it's going to require some outside intervention for it to go back. Okay. And temperature can have something to do with spontaneity, right? So depending on the temperature you're at, ice melting may be a spontaneous process or it may not, right? I mean, you look at Lake St. Louis as you're driving by. It was not a spontaneous process for that ice to melt for a long time because the temperature was so low, right? Once the temperature gets to 50 degrees, now it's a spontaneous process for the ice to melt, okay? So spontaneity depends on temperature. That's what I just said. Above 0, it's spontaneous for ice to melt. Below 0, it's the reverse. The freezing process is the spontaneous process below 0. So it kind of depends on temperature. Okay, so in a reversible process, all you have to do is basically exactly reverse the process, and you can put everything back the way it was, okay? Now, reversible processes would be like the equilibrium that we've been talking about, okay, for the last several chapters now. That's an example of a reversible process, okay? Most of the reactions that we had talked about up until that point are really not that reversible, okay? They're going to be spontaneous in one direction, typically. But in a reversible process, you can kind of go back and forth, okay? So an example of a reversible process, let's say, because we talked about above 0 and we talked about below 0, what about right at 0 degrees Celsius? Right at 0, you give a little bit of this ice just a little bit of energy and it melts, right? Take a little bit away and it refreezes. So right at 0, it's a reversible process going back and forth between ice and water, okay? So that's an example of that reversible process. An irreversible process, the only way you can get back is by doing work, okay? So you can't exactly reverse the change to the system. So an example of that, again, a situation I know you come across in your everyday life all the time, you've got a moving piston, a movable partition, and a box, right? And so you've got some, again, you've got the vacuum here, you've got the gas here. So you move the partition out of the way, okay, slide this up. The gas fills the entire container now, right? Now, we can get this back, with this setup, we can get back to our original, right? Because we can now move this piston over, push the gas back where it was, and now we've got a vacuum over here again, right? But this is not a reversible process because in order to do that, we had to do some work on that gas. We had to push against it, right? It's not something that can happen spontaneously in either direction, okay? A reversible process will happen spontaneously in either direction, okay? In an irreversible process, you've got to do some work to get it back to where it was. And it's not exactly the way that it was, right? Because now we've got this piston pushed in, and we've got a partition that's, up here. So this doesn't look, this last system doesn't look exactly like the beginning one did, all right? Spontaneous processes are irreversible, okay? So in other words, if it's spontaneous in one direction, you can't get it back without doing some sort of work or applying some energy, extra energy to it. Okay, so then we need to talk about entropy here. Entropy didn't know this. Rudolf Clausius. Sorry, I guess I'm laughing because very Christmassy name there, you know? You've got Santa Claus and Rudolph. Anyway, so entropy. And when you think entropy, I want you to basically think chaos. For the purposes of our class, we're going to be a little loose with our definition of entropy. Statisticians, mathematicians would not be very happy with the way I'm describing this, probably. The guy from Jurassic Park, what's his name? Malcolm, Ian Malcolm, is that his name? No? It's something not, anyway, yeah. He wouldn't be happy with the way I'm describing chaos either, okay? That was his big thing, was chaos theory. But entropy, basically just think disorder, okay? The more entropy there is, the more disordered the system is, the more chaos there is, all right? Some of you have rooms with a high degree of entropy in them, right? There's just chaos everywhere. Everything's thrown around, okay? Some of you have a very low degree of entropy in your room. Yeah. So, I mean, just think about that, okay? The more entropy you have, the more chaotic everything is. Well, and I hate to tell it to those of you who like to be organized, but the universe tends to move towards chaos. It's just the way it works. And you guys understand this, right? I mean, you don't do anything to clean a house for a little while, and all of a sudden it's like, what bomb exploded in here, you know, because everything's everywhere. And that just kind of naturally happens, right? Cars don't start running better over time. They break down over time, okay? So the universe tends towards entropy, okay? This is really not all that important. This equation, the Q reversible over T equation, I've always taught this before, and I think I'm going to kind of skirt over it this year because it's not on your equation sheet anymore. They just took it completely off. I think it used to be on there. I'm pretty sure they're not going to test you on this. I think they want you to know some of the big ideas about entropy and kind of understand what it is. And then there are some calculations we'll have to do with it later. But for right now, I don't think this is a big deal. So again, you can think of it as a measure of the randomness of a system. And again, systems, chemical reactions that tend to occur spontaneously will tend to be ones that increase the randomness of the system. They become more chaotic, okay? So the more chaotic something can become, the more likely it is to be a spontaneous process. And it's related to the various ways that molecules can move, okay? So the faster they're moving, the more entropy there is. The more of the particles there are, the more entropy there is, because it all has to do with the possibilities that can exist, okay? It's all about probability and statistics and all of that stuff, okay? Entropy is a state function, which means we can do some of the same things with entropy that we did with delta H, okay? So if you have two equations, you can do like a Hess's law thing where you can add the equations together. You can also add together their delta S's, just like you can with their delta H's, okay? And that's the main thing you need to remember from the state function idea. So if you want the change in entropy, you just, take your final minus your initial. If that delta S is positive, if there's more entropy at the end than there was to begin with, the universe likes that. If that delta S is negative, the universe doesn't like that so much. Now, you can get the universe to go that direction sometimes, which we'll talk about that more in a couple of days. But for a process occurring at a constant temperature, which is called an isothermal process, change in entropy is equal to the heat divided by the temperature, okay? The heat that would be transferred if the process is reversible. So again, this equation is not on your equation sheet. I don't think it's a big deal. I have you look at it, a sample problem in your book, just to kind of get an idea of how it works, but we don't really need to talk about it, okay? Do we get to the second law of thermodynamics for this particular? Is it? Okay, I need Okay, I don't think it cut out for too long. Anyway, second law of thermodynamics. Entropy is going to increase for a spontaneous process. All right, so I already told you this. The universe likes it when the entropy increases, when there's more disorder. Okay, so if you like an ordered life, you are fighting against the universe. I try to explain this to my wife sometimes. She doesn't get it. I'm just joking. I don't do that. But the entropy of the universe is not going to change for a reversible process. Okay, so delta S for a reversible process is 0. There is no net change in entropy for a reversible process. So guess what? Best you can do is not create any more chaos, right? That's the best you can do. In a spontaneous process, chaos gets worse, right? Or better, depending on whether you like it or don't like it. But chaos increases, I should say. For a reversible process, delta S is going to be 0, okay? Now, again, you can move things towards a greater degree of order. It's just going to require some energy in order to do that, okay? In other words, for reversible processes, the delta S of the universe is 0, okay? So the change in the system plus the change in surroundings is going to be 0. For an irreversible process, delta S of the universe is going to be greater than 0. So we're moving towards a higher degree of disorder. Okay? Oh, wait. Okay. Every spontaneous process that happens in the universe increases the entropy of the universe. All right? This universe at the beginning was very, very ordered, and now it's not. And it's getting worse. So, I don't know why I like this a lot. I just like this idea. Well, yeah, it kind of is philosophical, but I don't know why I like, am I the Joker? Why do I like chaos? I don't know. It's weird. Whoa. Boltzmann. I should look at my notes before let's see. Describe the concept of entropy on the molecular. Did we talk? Okay, now that's where I think we may need to cut off for today, because I think that's what we're talking about next time. Let me double check and make sure. Yeah, this stuff is all in 19.3. Okay, so really not a lot to the first two sections. It's just kind of an introduction to entropy. And we'll pick up some more tomorrow.